Most chemical reactions go one way. Once the products are formed, they do not react to reform the reactants. These reactions are said to be irreversible. The burning of sulfur in matches exemplifies this concept. Once the sulfur dioxide and heat escape, it is difficult to recombine them to reform the reactants. Unlike some other types of reactions, the moment the products are formed, they start to reform some of the reactants. These reactions are said to be reversible. The rate at which the products are formed is called the forward rate, and the rate at which the reactants are reformed is called the reverse rate. The following equation illustrates how reactants A and B react to form products C and D. Here is seen 1 mole of A is reacting with 1 mole of B to give a mole of C and a mole of D simultaneously. So we can say that the rate at which C and D are being formed is called the forward rate, and the rate at which C and D react to reform the reactants is called the reverse rate. At the very beginning of a chemical reversible reaction, because the concentrations of the reactants are high, its forward rate is high. However, with time, it slows down since the concentration of the reactants decrease. At the very beginning of the reaction, the reverse rate is slow since the concentrations of the products are very low. However, with time, it increases since the concentration of the products increase. At some point, the forward rate becomes equal to the reverse rate. Using the reaction above, we shall endeavor to illustrate how the change in concentration of the reactants and products change during a reversible reaction. At the very start of this reversible reaction, only reactants A and B are present. However, with time, their concentrations will decrease and the concentrations of the products C and D will increase. So you look at this other figure, we can now illustrate how that happens. That amount of reactants have disappeared and the corresponding number of moles of C and D has appeared. Again, with time, more of those will disappear. You can see smaller quantities of A and B have reacted to produce corresponding quantities of C and D. With time again, so we can see that with the passage of time, the concentrations of both A and B declined, while the concentrations of C and D increased. These curves here show you the rate at which A and B are decreasing, and these ones show you here the rate at which C and D are increasing. At the point in time when the forward rate becomes equal to the reverse rate, dynamic equilibrium is said to be established. The concentration of the reactants and products remain constant. However, at the molecular level, a minuscule number of reactant particles are still reacting to form products, and an equal number of product particles are reacting to reform the reactants. The system is thus said to be dynamic. The following curves would be obtained if the changes in concentration of the reactants and products for the above reaction are plotted and graphed. Starting with different concentrations of A and B, we will have the following curves up to the point where equilibrium is established. Notice how the rates of change in concentrations of reactant A and B are the same. This is so because their stoichiometric coefficients are the same, which is 1. Only one line is shown for the products, since they are both produced at the same rate as their stoichiometric coefficients are the same. Notice how when equilibrium is reached, the lines flatten out, since there are no change in concentrations of any species except for a few molecules that maintain dynamism. We have only drawn one line here to represent the products, because both of them are produced at the same rate. It is said that at this point where the lines flatten out, dynamic equilibrium is established. No change in the concentrations of either the products or reactants happens. Every different reversible chemical reaction will demonstrate its own pattern in changes in concentrations of its reactants and products with time. One of the factors that influences this is the stoichiometric coefficients of the reactants and products in the chemical equation. The reaction between hydrogen and nitrogen gases to form ammonia will be used to illustrate this concept. Notice how we are having 3 moles of hydrogen reacting with 1 mole of nitrogen to give 2 moles of ammonia. Notice how the rates of change in the concentration of hydrogen, nitrogen, and ammonia are according to the stoichiometric coefficients. The rate of decline of hydrogen is twice that of nitrogen, while the rate of production of ammonia is twice that of the rate of decline of nitrogen. Similar trends will be observed for other chemical changes at equilibrium. So the rate at which the reactants decrease and the products increase are governed by their stoichiometric coefficients. Equilibrium in physical changes. Unlike chemical equilibrium, there is what is called physical equilibrium. These are exemplified by the evaporation of liquids and sublimation of solids. To understand how this is achieved in liquids evaporating, we will study the following scenarios: the evaporation of water and the sublimation of naphthalene. Recall that according to the Maxwell-Boltzmann distribution of energy curve, at a particular temperature, not all molecules of a system have the same amount of energy, and only a small fraction of them have enough energy to react. If water is poured into an evacuated container and allowed to sit for some time, only those molecules at the surface with enough kinetic energy to break their hydrogen bonds will evaporate from the liquid and enter the space above. However, if the environment is less humid than in the container, water vapor will leave the container and enter the atmosphere. This will continue to happen until all the water is evaporated. But if the container is closed, as in System B, the water vapor molecules will aggregate above the water surface until saturation point is reached. At this point, the water molecules reform hydrogen bonds with each other and condense. Simultaneously, new sets of water molecules escape to form vapor. Equilibrium is reached as the rate of condensation becomes equal to the rate of evaporation. Something similar happens when naphthalene balls are placed in an evacuated container. Molecules with enough energy will sublime and escape as a gas and exit the container until all the balls disappear. If the container is closed, it allows the gaseous molecules to saturate the space above the balls. And finally, the molecules deposit to reform the solid naphthalene. Equilibrium is finally attained when the rate of sublimation is equal to the rate of deposition. Notice how only when the systems are closed, in both cases, equilibria are established. Equilibria cannot be attained in open systems. Homogeneous equilibria are those in which the reactants and products are in the same aqueous form or gaseous phases. The synthesis of sulfur trioxide, for example, is a homogeneous equilibrium since all the species are gaseous. That's a gas, that's a gas, that's a gas. The formation of methyl ethanoate from the reaction between ethanoic acid and methyl alcohol is an example of a homogeneous equilibrium since all the species are in their aqueous forms. Thus, aqueous ethanoic acid reacts with methyl alcohol to give you methyl ethanoate solution. Heterogeneous equilibria are those in which the reactants and products are in different phases. The decomposition of calcium carbonate is an example of a heterogeneous equilibrium in a closed system. This is solid calcium carbonate being heated to give solid calcium oxide and carbon dioxide gas. In a closed system, the carbon dioxide gas produced reacts with solid calcium oxide to reform calcium carbonate. The people who want to allow this reaction to go on to the right will deliberately allow the carbon dioxide to escape such that no equilibrium is established, and that results in eventual breakdown of all the calcium carbonate to give you calcium oxide and carbon dioxide. The electrolysis of water is another example of a heterogeneous equilibrium in a closed system. And this equation here illustrates how water is being electrolyzed to give hydrogen and oxygen gases. Of course, water is a liquid, and that represents two different phases. As such, it is described as a heterogeneous equilibrium. The equilibrium constant expression KEQ. Like I said before, at the point where equilibrium is established, there is no net increase or decrease in the concentration of either the product or reactant. So everything stays constant except for what is happening at a microscopic level. Norwegian chemists Cato, Gulberg, and Peter Wagee, having studied trends in reaction at equilibrium, noticed the constancy of the concentration of the reactants and products, and independently in the year 1864 formulated the law of chemical equilibrium or the law of mass action. It can simply be expressed as follows. At a particular temperature, for any chemical system at equilibrium, the ratio of the concentration of the reactants to the ratio of the concentration of the products remains constant. We will use the following general reaction to establish the basis for writing the equilibrium law expression Ke for reactions. So if you're having reactant A with that coefficient, reactant B of that coefficient to give product C with that coefficient and D with that coefficient, then the equilibrium constant expression can be represented as the concentration of product C raised to its coefficient C times the concentration of product D raised to its coefficient D divided by the concentration of reactant A raised to its coefficient A times the concentration of reactant B raised to its coefficient B. In this expression, the lowercase letters A and B are the stoichiometric coefficients of the reactants, and C and D are the stoichiometric coefficients of the products. To fully understand this concept, we shall do a few examples. So what do you think the K expression should be? Here we are only having one product, so we should take this product and raise it to its coefficient 2, and then do what? Divide that by SO2 raised to a coefficient 2 times the concentration of oxygen raised to a coefficient 1. You don't have to write that. So let's see what that is. If you said so, then you're correct. Let's see another one. You're having two products and one reactant. What should it be? It should be the concentration of PCl times the concentration of Cl, since the coefficients in both cases is 1, divided by this. What should this one be? What should be at the top? NH3 should be at the top, raised to the exponent 2. At the bottom, we should have hydrogen raised to an exponent 3 times the concentration of nitrogen. A point to note is this. Pure solids and pure liquids are not included in the equilibrium constant expression because the concentrations do not change during chemical changes. This is the point I want to make. We are having 4 cubes of a solid and together they weigh 8 grams. The total volume is 4 centimeter cube. The density of this is found by dividing the total mass by the total volume, which is 8 grams divided by 4 centimeter cube. So the density of the blocks is 2 grams per centimeter cube. If we remove one of the blocks, what is left is 3 cubes that weigh 6 grams. It will have a volume of 3 centimeter cube, and the density will be equal to what mass is there divided by its volume. And it will turn out to be the same as before. So we can liken the density of a solid to its concentration. If we remove a piece of a solid, its density doesn't change. As such, its concentration does not change. Same thing can be said for a liquid. We have 10 milliliters of water in this container here, and the mass of that is 10 grams. Its density will be equal to 1 gram per milliliter. If we remove 5 grams of the water, we will have 5 grams of it remaining with a volume of 5 milliliters, and its density will remain the same. So removing either pure solids or liquids in a change does not change their concentrations. However, if we have 10 milliliters of 0.1 mole per liter sodium chloride solution, and we evaporated 5 milliliters of water from it, we'll now have only 5 milliliters of it remaining. But of course, when you do the calculation, you're going to find because you have the same number of moles of sodium chloride in both cases, and you're having less volume here, of course, half the volume will give you twice the concentration there. So that is to emphasize the point that if you have aqueous solutions of acids and bases and other substances, their concentrations do change, but pure liquids and solids don't have a change in concentration. What kind of equilibrium you think this is going to be? They're not in the same phase. Both of these are solids. That's a gas. How do we express the KEQ expression? What do you say? These are pure solids, just the concentration of carbon dioxide. These are gases. That's a pure liquid. It's going to be equal to what? Hydrogen raised to that exponent and oxygen. Next, these are gases. That's a solid. This is not included. You're going to have ammonia into that. Thank you.